Imagine materials not found in nature, materials born from human ingenuity. These are metamaterials. They are artificial structures, carefully designed and assembled. Their true magic lies in their architecture, often at scales smaller than the wavelength of light itself. This intricate construction gives them extraordinary properties, allowing them to interact with light, sound, and other waves in ways that conventional materials simply cannot. Think of them not as just new substances, but as new ways to command the forces of nature. We are no longer just finding materials. We are inventing them, crafting their abilities from the ground up, opening a new chapter in our cosmic journey of understanding and manipulation. How do these metamaterials achieve such feats, you ask? It's all about their structure. These are not uniform blocks of stuff. Instead, they are composed of tiny repeating units, meticulously arranged. Each of these meta-atoms interacts with electromagnetic waves, like light, in a specific way. When combined, these interactions create a collective behavior that can steer, bend, absorb, or even amplify waves with astonishing precision. It's like an orchestra where each tiny instrument plays its part to create a grand symphony of light manipulation. This allows us to build devices that can perform optical tricks previously confined to the realm of science fiction, all by carefully engineering patterns invisible to the naked eye. Enter transformation optics. This is the brilliant design philosophy, the intellectual toolkit that allows scientists to dream up these light-bending structures. It's a concept that sounds like it's straight out of a cosmic playbook. Transformation optics uses the mathematics of general relativity. Yes, Einstein's theories about how gravity warps space-time, but applies it to light. Imagine bending the coordinates of space, conceptually speaking, to define a desired path for light. Then scientists use these transformed coordinates to calculate the specific material properties needed at every point to make light follow that exact path. It's like being an architect for light itself, designing its journey through a custom-made landscape. Now you might wonder, does this mean we are breaking the old rules of optics, like Snell's law, which tells us how light bends when it goes from air to water? Not quite. Snell's law and other classical optical principles are still fundamental. Transformation optics doesn't discard these laws, particularly the foundational Maxwell's equations that govern all electromagnetic phenomena. Instead, it provides a powerful framework to design materials with such complex, spatially varying properties that light behaves in ways far beyond what traditional, uniform materials allow. It's not about breaking the rules of the universe, but about understanding them so deeply that we can achieve outcomes that once seemed impossible, guiding light with unprecedented freedom. One of the most mind-bending applications of transformation optics is its ability to mimic cosmic phenomena right here on Earth. Consider black holes, those enigmatic cosmic vacuum cleaners whose gravity is so intense that not even light can escape. Using metamaterials, scientists can design optical black holes. These aren't real black holes, of course. They don't have crushing gravity. Instead, they are structures that absorb incoming light from all directions, guiding it to a central core from which it cannot escape, much like their celestial counterparts. This allows us to study the behavior of light in extreme gravitational fields, but in a safe, controlled laboratory setting, offering a tiny window into cosmic mysteries. Then there's gravitational lensing. Out in the cosmos, massive objects like galaxies bend the fabric of space-time. Light from distant objects passing nearby follows this curvature, creating cosmic mirages, multiple images, or arcs of light. Metamaterials, designed using transformation optics, can replicate this effect on a much smaller scale. They can be structured to have a refractive index that varies in just the right way to bend light around a central region, making objects hidden behind it appear distorted or even invisible, just as gravity lenses light in the universe. We can create these lenses that mimic the universe's grandest optical illusions, allowing us to explore phenomena that are light years away. The universe is filled with complex, dynamic systems, often exhibiting chaotic behavior. Think of the swirling patterns in Jupiter's atmosphere or the intricate dance of stars in a galaxy. Metamaterials can also be designed to create complex environments for light, where its pathways become incredibly sensitive to initial conditions, leading to chaotic scattering. By studying how light behaves in these engineered chaotic landscapes, we can gain insights into the fundamental nature of chaos itself, a principle that governs systems from the weather on Earth to the large-scale structure of the cosmos. It's another way these remarkable materials connect our terrestrial experiments to the universe's vast and complex workings. Beyond mimicking cosmic events, transformation optics allows us to design something called continuous index photon traps. Imagine a material where the ability to bend light, its refractive index, changes smoothly from point to point. Such a material can be designed to guide light into a specific region and then effectively hold it there. Light entering these traps can be dramatically slowed down, its energy spiraling inwards until it's confined. This is akin to how gravity can trap matter, but here it's done with carefully engineered optical properties. The ability to slow, stop, and store light opens up incredible possibilities for information processing, energy storage, and highly sensitive detectors, a true command over light's journey. Let's talk about lenses. For centuries, we've used curved pieces of glass to focus light to see the very small or the very distant. But traditional lenses have limitations. Gradient index, or GRIN, lenses offer a different approach. Instead of relying on curved surfaces, GRIN lenses have a flat surface, but the material itself changes internally. The refractive index, the property that determines how much light bends, varies gradually across the lens. This internal variation is what focuses the light. It's like having a multitude of tiny different lenses seamlessly integrated into one piece, offering new ways to shape and direct light with greater control and fewer aberrations. Transformation optics takes the concept of GRIN lenses to a whole new level. It provides the mathematical tools to design GRIN lenses with capabilities far beyond what was previously possible. We can create lenses that are incredibly thin and lightweight, a huge advantage for portable devices and complex optical systems. More excitingly, we can design lenses with entirely new functionalities, like focusing light to incredibly tiny spots, or creating lenses that can see around corners, metaphorically speaking. This design power allows us to overcome the traditional trade-offs in lens manufacturing, pushing the boundaries of what optical components can achieve, shaping light with unprecedented finesse. The implications of such advanced light control are vast, especially in challenging environments like the battlefield. Imagine soldiers equipped with sensors that can see incredibly tiny details, perhaps detecting hidden threats or analyzing microscopic samples on the go. Metamaterial-based lenses could lead to imaging systems with resolutions far surpassing current technology. Improved sensors, built with these principles, could offer enhanced night vision, the ability to see through fog or dust, or even detect subtle chemical signatures from a distance. This isn't just about seeing better. It's about gaining a decisive informational advantage through superior manipulation of the electromagnetic spectrum, potentially saving lives. And of course, there's the captivating idea of invisibility. While true, perfect invisibility cloaks remain a significant challenge, transformation optics and metamaterials are the scientific foundation for this pursuit. The concept is to design a material that can bend light waves smoothly around an object, like water flowing around a stone in a stream. If light doesn't scatter off the object, and instead reforms perfectly on the other side, the object becomes invisible to an observer. While current demonstrations are limited to specific wavelengths or small objects, the theoretical framework is sound, pointing towards a future where we might manipulate light to render objects or even people undetectable. The journey into metamaterials and transformation optics is just beginning, yet the horizon is already sparkling with transformative potential. Consider night vision technology. Current systems amplify existing faint light, but metamaterials could lead to devices that are far more sensitive, perhaps even capable of constructing images from the faintest thermal signatures or scattered photons with unparalleled clarity. We could be moving towards true seeing in the dark, where the limitations of human vision are overcome, not just by amplification, but by fundamentally new ways of capturing and interpreting the electromagnetic information that surrounds us, even in the deepest night. Beyond vision, think about communication. Our modern world runs on information, much of it transmitted as pulses of light through fiber optic cables. Metamaterials offer the potential to create optical components that can route, switch, and process light signals with incredible speed and efficiency, all on a microchip. Imagine data transmission rates orders of magnitude faster than today, with significantly less energy consumption. This could revolutionize everything from the internet to supercomputing, allowing us to connect and process information on a scale that is currently hard to fathom, building a more interconnected and intelligent world. These new tools for controlling light will also undoubtedly revolutionize scientific discovery itself. Imagine microscopes that can see individual molecules in living cells without damaging them, or telescopes that can resolve details on distant exoplanets with unprecedented clarity. Metamaterials could enable new types of sensors for detecting gravitational waves with greater sensitivity, or for peering into previously opaque materials. Every time humanity has gained a new way to control light, from the first lens to the laser, it has opened up new vistas of understanding. Metamaterials and transformation optics promise another such leap, giving us sharper eyes to explore the universe, from the infinitesimally small to the cosmically vast. The adventure with metamaterials is a testament to human curiosity and our relentless drive to understand and shape the universe around us. We are learning to speak the language of light, to coax it, bend it, and guide it in ways our ancestors could only dream of. From mimicking the grand dramas of the cosmos to designing practical tools that can change our daily lives, the principles of transformation optics are unlocking a new reality. The future will likely see devices and technologies based on these principles become commonplace, integrating seamlessly into our world, a world where we have truly mastered the art of weaving with light. The cosmos is full of wonders, and we are just beginning to create some of our own.